have a look at the integrity from today. So in the cryptographic session, we had a look at the cryptographic algorithms and then the way they actually were, the block cipher, stream cipher, the block size, etc. And the other part of the cryptography is the integrity. Integrity is going to address the modification part of the data. So the cryptography addresses the secrecy, for example, the confidentiality for the data. The integrity deals with preventing the modification, not preventing the modification, rather than it's a reactive control or detective control, basically. Okay, when I say detective control, when somebody modifies the data, you will be in a position to get to know whether the data has been modified or not. The data modification could have happened through an authorized user or unauthorized user. Authorized user through an authorized mean is actually okay, but authorized user through an unauthorized mean is actually not okay. Okay, for example, if I'm a teller in a bank and when there is a withdrawal request, okay, if I'm going to take few pennies with me, and over the period of time, there is going to be a substantial amount. Okay. Now, this could be like salami slicing attack. This is called salami slicing attack, where I don't make a fortune from a single transaction, rather, transactions over a period of time. Okay, so it's called salami slicing attack. This is also an integrity problem, wherein I'm an authorized user and I'm committing a crime, which is an integrity issue over the period of time. So the integrity is to prevent unauthorized user from modifying the data, and to prevent the authorized user from modifying the data in an unauthorized way. So they both are, the integrity issue. And the integrity is of data integrity and system integrity. And obviously, system integrity is more on the overall physical system or the virtual system, whatever it is. Okay? It deals with the application integrity. And data integrity, obviously, only the authorized person should be in a position to modify the data. So only the authorized person should be in a position to modify the application also. So that becomes a system integrity. Okay, so integrity falls under two categories. Now, just to have a recap on what this man in the middle attack is. Okay, we have something called the sniffing. Sniffing is an attack challenging the confidentiality, wherein there is an intruder in the middle, and he's going to sniff the data and learn what the data is all about. Modification is the intruder is going to, the man in the middle, or rather, the intruder is going to modify the data between the source and the destination. Sniffing it, like the popular movies of yesteryears, the hero will fight every single person in the world. Okay, he is a very brave guy, but he does not have the guts to propose to his girlfriend, and he's going to give the letter to his friend, who's a comedian, but he's the actual antagonist in the movie. He's going to open the letter and read the letter before handing it over to the heroine. Okay, so this is sniffing. If the hero is going to give the letter to the comedian and asking him to deliver it to the heroine, and the comedian opens the letter and says, "I love you," but the comedian is actually going to add a word "not," "I love you not," and hand the letter to the heroine. This is modification. So the actress, the main female lead, will be crying for the entire movie until the climax, where she learns that the letter has been modified by the antagonist, who is the comedian. Okay, and what is the interception? Interception, the data or traffic does not reach the destination. That means the hero is actually going to give a love letter to the antagonist. Okay, who's a comedian. The comedian does not deliver the letter to the heroine. There is interception. What is spoofing? The comedian is going to write a letter as if it's been written by the hero, and he's going to give it to the heroine. Okay, that is spoofing. Okay, so it's a source or an authentication problem. Interception is the availability problem. Modification is the integrity problem. Sniffing is a confidentiality problem. So replay is also a source of an authentication, wherein the intruder is going to listen to a traffic that has actually happened on a system in some time past, and he's going to produce the same transaction. It could be your authentication transaction also. What is the hijacking? So I'm in the hijacking, in the replay. Okay, coming out of the same example, the comedian is going to write a letter, and he understands the handwriting of the hero, before handing it over to the heroine. Then he writes another letter of the same handwriting and gives it to the heroine saying, I love you or not. Okay, there's a replay attached. Now, what is the hijack actually? In the hijack, it's very similar to the modification. Okay, hijacking is more towards a source of an authentication in this particular context than the modification. There's a conversation between A and B, but the intruder comes in the middle and he's going to speak to B, okay, the heroine, as if he's the hero. Okay, that's hijacking. So hijacking is authentication is established, then the traffic is actually hijacked. Okay, in a way, the cross-site request forgery, okay, that we are going to have a look at when we discuss about the application security is also an hijacking attack. Okay, now coming on to the man in the middle attack. Okay, now let's have a look at that with an illustration. Okay, so before we get on to the message integrity protection. Okay, now coming on to this particular one. Yeah, now A has got a message. Okay, and A is subjecting the message to the hashing algorithm, and A is going to receive a hash value, and the message plus the hash value is actually sent to B. Okay, one thing we should always understand here is the message and the hash value is actually not encrypted. That means anybody can actually look at this particular traffic, okay, in the transit. Okay, we are not speaking about the encryption at all. We're just speaking about the hashing. Hashing is a detective control to find out whether the the message has been modified or not. Now coming on to C, C is the man in the middle. Okay, MITM, and he's going to do what is called a modification. Okay, so he's going to modify the message plus the hash value to message 1. He's going to calculate the hash value for the message 1 using the same algorithm. Okay, let's say MD5, and he's going to get hash 1. So message 1 plus hash 1 is actually sent to B. Okay. Now at the B receives message 1 plus hash 1. B is going to do a substring operation, get the message 1. Okay, and B is going to subject the message 1 to MD5, hashing algorithm, and he or she calculates the hash 1. Okay, so if hash 1 that B has calculated is equal to hash 1 that B has received, that B's message has not been tampered with the transit. But in this particular scenario, B does not know that the message has been tampered, okay, in the transit. It's coming from C and not A. So as far as B is concerned, the message has not been modified because B has calculated the hash value. But B does not know the message has come from C but not A. Now, the scenario, we'll call this a scenario 2. We'll call this a scenario 2. Excuse me for my bad spelling. Yeah, in scenario 2, what A is actually going to do is A is going to get the message and A is going to calculate the hash value of the message. A is going to calculate the hash value of the message using symmetry key of A and B. Me and my lofty fingers. Okay, plus the symmetry key used between A and B, and what we get is actually was a message authentication code called MAC. So the message plus MAC is actually sent to B. Okay, now there's a man in the middle called C, and C is going to get message plus MAC. Now C wants to actually calculate, okay, he's going to modify the message. Let's say he's going to modify the message as message 1. And C wants to calculate the message authentication code. Unfortunately or fortunately, C has got the symmetry key used between A and C and B and C, not between A and B. Because symmetry key used between A and B is going to be either with A, okay, it's going to be with A and B, okay? And, as far as C is concerned, it has got 2 symmetry keys in this scenario. And this symmetry key is used between A and C and B and C. Okay, not between A and B. So this situation is not possible. Now, when it goes to B, so B is going to have the message plus the MAC, message plus the message authentication code. B is going to subject the message to the hashing algorithm along with the symmetry key used between symmetry key used between A and B. Okay, so B is going to calculate the symmetric key message authentication for the MAC that was sent is equal to the MAC that has been calculated. Okay, so if this is the case, then B knows that the message has not been tampered in the transit, and B also knows that okay, it has come from A because it's used to it got the MAC, the same MAC using symmetric key used between A and B. If C, then B knows that okay, and by using symmetric key between A and B, it cannot calculate the same MAC. So B can identify that the message is not from A. You have to use different keys to identify from who the message is actually. And eventually B will find out the message is actually from C. Now scenario 3 is very important. Okay, scenario 3 is very important. Okay, scenario 3, what actually happens is that A, you got the message, and A is going to calculate the hash value of the message, and you get you subject MD5 or SHA1, SHA2, whatever the algorithms. You get the hash value, and A is going to encrypt the hash value using private key of A. Okay, encrypting the hash value with the private key of the sender is actually called as a digital signature. Now we should always understand that the digital signature of A is dependent upon the hash value, which is in turn dependent upon the message. You cannot have a constant digital signature for a variable message. Correct? I am CISSP certified as a message, then I calculate the hash value, it is of a certain value, then I encrypt that with the private key. Okay, I get a digital signature. Okay, private key is sender, I get digital signature. I am CSSLP certified is a different message altogether. So hash value will also be different. And encrypting the hash value, the private key will also give me a different digital signature. So the digital signature is not a constant one, it's a variable one, depending upon the hash value, which in turn depends upon the message. So let's call this hash value as DS of A for now. Now what I'm going to do, what the sender will do is message plus DS of A together is encrypted with the public key, okay, of B, who's the recipient in this particular scenario. Public key of B, recipient in this particular scenario. Let me have an other bracket here. Okay. Okay. Now I'm going to get this is the final message. Okay. This actually gets onto the network. Okay, and then it has to travel to B. At B, okay, what happens is okay, I get the complete message. Because the final message is encrypted using the public key of B, the B will use the private key of B. Okay, and then to decrypt it. So these two will get nullified, and what I actually get is message plus digital signature of A. Now, what is the digital signature of A? So digital signature of A is nothing but encryption of the hash value of the private key of A. Okay, so DS of A is equal to this one is equal to. So what B can actually do is, okay, he can decrypt this particular message using public key. Public key is accessible. Public key of A. Public key of A. So these two get nullified, and all I get is the hash value. Now what I'm going to do is I'm going to pick up the hashing algorithm, subject the message to the hashing algorithm, calculate the hash value. If hash value computed is equal to the hash value that has been sent by A, now that integrity is also established. That means the message has not been tampered with the transit. Calculating the digital signature, it will establish the source origin authentication, non-repudiation, accountability, and encrypting this particular one, and calculating the hash value will establish integrity. Encrypting the final message with the public key of the recipient will establish confidentiality. So in this scenario, we establish integrity, confidentiality, source origin authentication, non-repudiation, accountability. Availability is a principle that needs to be established in the infrastructure. So this scenario 3 is going to address all the 5 important principles of cryptography: confidentiality, integrity, source origin authentication, accountability, and then non-repudiation. Having said that, let's have a look at the few of the algorithms that are available for us for the hashing and the avalanche collision. What is the collision attack? What's an avalanche effect? What's the birthday attack on the next video? And then we will get on to the digital certificates part of it. Okay. So thanks for joining me for this video, and then stay connected by subscribing to my channel Happy learning and wish you all the best for CSSP. Cheers, everybody.